Building the International Space Station was a huge effort. The early stages of construction involved putting together the pressurized modules where astronauts can live and work. But for this video, let's take a look at building the integrated truss structure. You can think of this like the backbone of the station, holding everything else together. Building the truss took more than 10 space shuttle missions, and more than 9 years to complete, with a few problems along the way. Okay, so picture this. It's 2007, and they are moving a large piece of the truss called P6 to its final location. But when they unfolded the solar array, it ripped. It's way out there on the end, and there are no spare parts for this. This led to one of the most daring spacewalks ever attempted. But before we can cover this story, we need some background. Let's zoom out for a moment. This is what the station looked like when they completed it in 2011. Today it looks mostly the same. You'll see a few extras like these solar arrays. But let's keep things simple for now. The integrated truss structure spans more than 100 meters. That's about as big as a commercial airplane. The truss is the longest structure ever assembled in space. Here's the major parts that are attached to it. The 8 solar array wings to power the station, radiators to cool the station, batteries to store power, external storage platforms for storing extra parts, and the robotic systems for moving things around the station. But why a truss at all? It was a design choice very specific to the space shuttle era. But keep in mind that the space shuttle retired in 2011, right after the station was complete. Each module on the station could have been built with its own power and cooling. But instead, NASA decided to build these systems on a large frame called the truss. The truss could then be separated into sections, and these sections fit just right in the shuttle's payload bay. Each truss segment is numbered based on the center of the station. P1 through 6 are here, S0 through S6 are here. P stands for port, or the left side of the station, and S stands for starboard, or the right side of the station. The center truss segment, S0, is the one that connects to the pressurized modules down below. This is where the astronauts live. If you look closely at the segments, there are 2 missing numbers, P2 and S2. After other countries joined the program, these were canceled, and instead we added the Z1 truss. Z stands for zenith, which is the space-facing side of the station. This is why it's called the Z1 truss. Most of the pieces of the station were brought up by the space shuttle, but not all of them. Let's take a look at the early stages of construction. It started in 1998 with Zarya, launched by a Proton rocket. Then Unity, this was the first piece brought up by the space shuttle. Then the Zvezda service module, launched by a Proton rocket. Z1 and PMA-3 were then added by the space shuttle. Z1 is not part of the main truss, but it was essential in the early stages of construction. Once Z1 was installed, astronauts were able to start living aboard the station permanently. They usually spend about 6 months aboard the station before another crew comes up to replace them. Notice how the station sometimes has other visiting spacecraft, bringing new crew members and supplies. Now, at this point, we're ready to start building the main truss structure. In this video, we're going to go through quite a few space shuttle missions to show how this worked. And the last one had some of the biggest problems. But let's start at STS-97. This mission brought up the first large piece of the truss. In December of 2000 was STS-97. Remember that STS stands for Space Transportation System. It's how NASA numbered space shuttle flights. This is the Space Shuttle Endeavour. The P6 truss segment can be seen inside of the payload bay. P6 is the very end piece on the port side of the station. But since this was the first truss piece, it was temporarily mounted on Z1. Now, when they attach pieces of the truss, the mechanisms are similar, but there are a few different types. Don't worry, you won't need to memorize these acronyms. Let's start with the one at the very end, the Rocketdyne Truss Attachment System. This was first used to attach P6 to Z1. There are 2 sides to this, an active side and a passive side. You can see the matching cups and cones. The 2 sides fit together just right, and then the capture latch in the middle to secure it in place. Before any of this could happen, they had to get P6 out of the payload bay. The shuttle's robotic arm is called the Canadarm. And yes, it is made by our friends from Canada. This was operated by an astronaut from inside the orbiter. As the 2 segments came together, astronauts confirmed the alignment and used tools to close the capture latch, and then drive 4 structural bolts to rigidly lock the truss in place. Astronauts then connected power, data, and cooling lines. They also deployed radiators to cool the station. Then it was time to deploy the twin solar arrays. Each side is 33 meters long, but for the launch into space, they were folded up at the very end. Then it was time to rotate them out, and the arrays were stored inside of the blanket boxes. When the first array began to open, there were some panels that stuck together. Some of the sections would suddenly snap apart, rippling down the array. This actually knocked the tension cables loose at the base, which could mean a floppy solar array. This could pose a lot of danger to the growing station. So NASA sent astronauts out on a spacewalk to reattach them and carefully opened the array to its full length. For the second array, they decided to go a lot slower. The trick was pausing every so often to allow the sunlight to warm the panels. The station had its first major source of power, but this wasn't the last time that P6 would cause problems. In total, 37 shuttle missions visited the International Space Station. 10 of those flights assembled the truss. Truss segments were built in several different cities in the United States. Like most space station components, they were shipped to Kennedy Space Center in Florida for the final processing and launch preparations. You might be familiar with the Vehicle Assembly Building, or VAB. This is where rockets are assembled for NASA. Several miles south of this is the Space Station Processing Facility. Most space station parts were processed in this building. In the early 2000s, it was packed with all sorts of parts and equipment. You can see many of the truss segments and pressurized modules waiting to be launched to the station. When they were ready to be sent to space, they were loaded into the payload canister. And then the doors were closed. And in another building, it was gently rotated to the vertical position. And then it slowly made its way to the launch pad. This is the rotating service structure. The canister was hoisted up and the payload was transferred. And the structure would then rotate around to the shuttle. The payload was then installed inside of the orbiter. Let's fast forward through the next few modules. Three shuttle missions in 2002 were dedicated to begin building the Large Truss backbone. S0 would be the first. It was added in April 2002 during STS-110, using the Space Shuttle Atlantis. Remember that the P6 truss was installed in a temporary location, but the S0 truss is permanently installed. It's designed to anchor the rest of the truss structure. To do the heavy lifting, they used the Canadarm2. This is a robotic arm that was very similar to the Canadarm on the shuttle, but a little bit stronger. This was a very slow process, being careful not to damage anything. S0 was mounted on top of the US Destiny laboratory. The mechanism they used is called the Module to Truss Segment Attachment System. The active side has 4 alignment guides and a capture latch. The passive side has matching interface bars and a capture bar. The Canadarm2 slowly moved it in position. First they did the latch, and then 4 bolts to secure it in place. They added several struts for reinforcement. S0 included a mobile transporter that runs on rails. On the next shuttle flight, they added the mobile base system. This allows the Canadarm2 to be able to move to different locations across the truss. The next truss segment was S1. This happened in October 2002. The mobile base system moved to the very end of S0. Then the Canadarm2 could grab S1 from the shuttle payload bay. These types of operations took hours to complete. Astronauts controlled the movement from inside of the Destiny module. To connect the truss segments, NASA used the segment-to-segment attachment system. It works very similar to what we've seen before. There are several alignment cups and cones, as well as 4 motorized structural bolts. This time, the active side is fully powered, with no need for astronauts to manually drive the capture latch and bolts. Once installed, S1 was brought fully online during a series of spacewalks. And just 1 month later, the P1 truss segment was installed. Each of these segments carries 3 large radiators, which can unfold once in orbit. These radiators remove heat into the vacuum of space. Without them, the station would overheat. At this stage in assembly, only 1 radiator on each side was needed. Things were going very well with construction until February 1st, 2003. It was a science mission that did not go to the space station. At the end of the mission, they didn't know that the heat shield was fatally damaged. As they re-entered the atmosphere, the space shuttle Columbia was destroyed. All 7 astronauts were lost. NASA stopped flying the space shuttle for almost 3 years while they figured out how to prevent this from happening again. During this time, the Soyuz spacecraft was the only way to get to and from the space station. When the shuttle missions finally resumed, the space shuttle carried new safety upgrades, including the Orbiter Boom Sensor System, or OBSS. It was designed to extend the Canadarm on the shuttle. Then they would scan underneath to see if the heat shield had any damage. The boom would later play a key role in one of the truss's most difficult repairs. Then finally, after more than 3 years, they brought up the next piece of the station, the P3-P4 truss segment. This involved a very careful handoff between the Canadarm on the shuttle and the Canadarm2 on the station. This was attached once again using the segment-to-segment attachment system. Over multiple spacewalks, astronauts unfolded the radiator and successfully deployed the solar arrays. This time, they made sure there were no problems. The most important part of this truss segment is the Solar Alpha Rotary Joint, or SARJ. This large rotating joint allows the solar arrays to spin like a windmill. The solar arrays also have beta gimbal assemblies, which can rotate independently. This allows the solar arrays to track the sun and generate as much electricity as possible. Let's take a look inside of the SARJ. The trundle bearing assemblies support the rotating joint. There are 12 of these. They allow the race rings to spin smoothly. There are 2 drive lock assemblies. This is what rotates the race ring and then locks it in place. In the center is the utility transfer assembly. This is where the power and data lines go through. This is all on the P3-P4 segment. Later on, they would install a very similar segment on the other side. That means there is a SARJ for both sides of the station, allowing for lots of movement for the solar panels. But shortly after the starboard side was installed, they started seeing problems. During a spacewalk, they found metal shavings and signs of physical damage on the outer race ring. There were a few issues with the trundle bearings. The SARJ was repaired in space during 2008. Astronauts cleaned the joint, replaced the trundle bearings, and applied some new grease that works well in space. The port SARJ was fine, but it was also lubricated just to be safe. It was very important to be able to rotate these solar arrays. Let's back up in time just a little bit. We've got 1 set of solar arrays on the port side, and P6 is still on top. This is an issue because the truss can only rotate so much before they run into the P6 arrays. They would need to retract the port side solar array. Next up is the Space Shuttle Discovery with the P5 truss. They moved P5 once again using both robotic arms. P5 is a very short truss piece. It's connected using the modified Rocketdyne truss attachment system. There's no capture claw in the middle. This time the connection will be made on the corners with spring-loaded pins. This works similar to how a latch works on a door handle. The astronauts were then able to manually drive the bolts. Then it's time to retract the port side array up above. This turned into a multi-day task. The panel snagged and folded the wrong way, which delayed the whole process. P6 is once again causing trouble. One thing they tried was shaking the base by hand. That helped a little bit, but the ultimate solution was to lift one of the astronauts using the Canadarm2, and then use an improvised tool that they called the cheater bar. It was used to free the stuck sections, and then finally the array could go all the way in. In June 2007, they delivered the S3-S4 truss. then retracted the P6 starboard array. This time, the process went much better. Then August 2007, the S5 truss. The station is starting to look like the ISS we know today, but we still need those outer arrays. One of those outer arrays is P6. It's finally time to relocate it. Under normal circumstances, this was already a complex mission. The flight delivered Node 2, or the Harmony module. This was temporarily installed to the port side of Unity. Later, it would be relocated after the shuttle left. But the major challenge of this mission was P6. Its radiators and solar arrays had already been retracted on earlier flights. Astronauts had to manually unbolt it, then slowly move it using the Canadarm2. This took a while to complete, with a bit of a handoff between the Canadarms. Spacewalking astronauts then helped make sure that P6 was aligned perfectly. And then they manually bolted it together. Then, once the radiator was deployed, it was time to unfold the two solar panels. The first array deployed, and there were no issues. The second one, well, before it was complete, they had to stop the deployment. Astronauts noticed a tear between the panels, at first hidden by poor lighting. But how did this tear happen? Let's get a close-up look. There is a guide wire that runs along the panels as they unfold. This wire had a snag in it. It was caused by fraying on the wire. As the panels opened, the snag got stuck on the hinge. This is what caused the tear. The deployment had to be stopped so it didn't get any worse. NASA engineers and astronauts worked for several days to design a fix using only what the astronauts had on board the station. First, they would need to cut out the snag. The crew members in space would craft cufflinks to repair the torn section. These were made of aluminum strips and spare wire. The array has tiny holes that kept it aligned during the launch. The cufflinks would need to be threaded through the holes by hand, and then they can keep opening the array without any more stress on the tear. But there's another problem. Even when they moved the mobile base system to the very end, the Canadarm2 couldn't reach the damaged section. The solution? Do you remember the orbiter boom sensor system from earlier? It was specifically designed to take a look underneath the shuttle. But this time, NASA mounted it to the station's arm, and one of the astronauts was sent to the very end to perform one of the most delicate spacewalks, getting some incredible views along the way. He was the tallest astronaut on board, and even then, he could barely reach. Once at the solar array, he installed the cufflinks. They used another special tool that they called the hockey stick to avoid touching the solar panels and getting shocked by electricity. There was a lot of delicate handwork involved here. Another astronaut nearby kept a close watch on him, being his second pair of eyes. After installing the cufflinks, the astronauts closely watched the panels as they deployed the rest of the way. This spacewalk lasted for more than 7 hours. The solar array was saved, and it still remains in use today. The orbiter boom was so helpful that NASA left one permanently on the station just in case it was ever needed again. In the coming years, they installed more pressurized modules and the S6 truss segment. This officially completed the station's truss. With all the arrays deployed, the station is able to generate enough to power more than 40 homes on Earth. This allowed the station to continue growing to its full size. In recent years, solar technology has come a long way. They installed the Roll-Out Solar Arrays, or iROSAs, starting in 2021. These are more efficient than the original solar arrays. Today, if they designed a space station, it would probably look a lot different than this, but the truss will go down in history as an icon. It will remain a symbol of what nations can build when they work together.